Hello everyone, it's July 13th. Kind of have to do the LeetCode today at night because I had other obligations during the day. Well, I collected some data for my study and it was raining. Well, it's not the most pleasant experience. Anyway, let's take a look what we have today. Nothing to worry about here. Find peak element. Mountains. A peak element is an element that's strictly greater than its neighbors. Given an integer array, find the peak element and return its index. If the array contains multiple peaks, then return the index to any of the peaks. Hold on, return one index? Return the index of any of the peaks. You can imagine that numbers -1 and this, okay? You must write algorithm that runs the all log n time. So 3 is the peak. Here, either index number 1, where the peak element is 2, or index element 0, 1, 2, 3, 4, 5. Okay, so length is 1000, number is gigantic, and adjacent numbers are not the same. I mean, ON solution is quite straightforward. We just check, check, check. Whenever it drop, that is a peak, right? And then when it drop, we just keep going as the down edge. And I think there are. I'm thinking about the regular solution for checking peaks. I think it's what do I call it? A peak going up, 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 right? And then when it's small coming in, when it's big coming in, and hold on, what is the data structure I'm thinking about right now? The data structure I'm thinking about right now is we'll record all the peaks, which is, I remember it's something like a monotonic array, right? So if it's bigger than previous, we just append. If it's smaller, we don't care. Smaller, we don't care. And no, if it's bigger than previous, then I will, it's bigger than that, I'll pop, pop until I cannot pop anymore, right? Then if it's small, I append. Yeah, if it's small, I append. If it's bigger, I will pop until I cannot pop. So this will guarantee that we will obtain all the large values, but those are not peaks, right? We'll obtain all the, um, we'll obtain the like adjacent peaks. That's what we're gonna obtain. Adjacent peaks. Yeah, that's what we're gonna obtain. So as it gets smaller, we just keep going. Once it gets larger, right? Once it gets larger, and then we just pop, pop, pop until I cannot pop anymore. I cannot pop anymore. And then every time I do that, we can I was thinking about holding water, the holding water problem. It's different. This one is different. Anyway, so we can definitely just go up, just count, right? So go up. Next value is larger than previous, and then when it starts to drop, then we pick that out, right? We pick the peak out, and let's say you can return anything, which means we just need to run it, and then we find the first peak, then we return. But that's not log n time, right? I mean, worst case scenario, if we just do linear to check, Yeah, it's like on the down edge we just reset to 0, and then on the up edge we set it back. Yeah. So the worst case scenario is if the well, what if we don't have it, right? What if we don't have a peak? Let's say this. What are you going to do with that? What's the peak in this? 2, because the last one is expected to be, so either the first one or the last one. Okay, that makes sense. The worst case scenario is this one, right? Everything else we can find out before iterating through all n situations. Okay, so here's what I'm going to do. Right, first of all, while I still have this idea, I want to do it not O(n) log n, not log n, just O(n). Now we can try the O(n) solution to see if it passes. Right? Maybe it'll pass, and then we at least can finish today's challenge. And then we try to figure out how O(n) is going to work. So O log n is going to work. Man, I am not good at night. Brain is just not functioning at the same pace. It's a bit slower right now. All right, so we're gonna do O(n), which is not recommended. We're gonna have a flag for the upward equals true because initial value is minus infinity, so always upward is true. And then we're just gonna say for I in range 1 to len nums, right? Because it's upward, we know O0 will be an upward. So we can directly compare. We say if nums I is smaller than nums I minus 1, right? That means it's and upward. Then we return I minus 1. I minus 1 is the peak, right? Otherwise, aleph nums, let's write it out. So if, okay, let's not do this. Let's do this. If upward, then we find the peak, right? Else, if upward, we find the peak. Else, then we don't do anything, right? That means I is smaller than previous one. We already set it to down. Then there is no down because we're going to return the first peak. So if it goes down initially, right? If it goes down initially, enjoy. Then the first one is the result, like 3, 1, 2, 3, 1. That way I can return the first one. I can return 0. Yeah, I can return 0. So there's no downwards. It's only upward, right? It's only going upward. So if it only goes upward, that means, if it only goes, that means the first decrease, right? The first decrease is the one we're gonna look for, right? So we basically can just go through and find the first decrease. We go through, if it has a decrease, then if it's increase, we don't care, and then the first decrease. So we don't even need this, right? We don't even need this. We just go through this, the first one, then we return, right? And if not, like after the entire thing, everybody is larger than the previous one, then we return the last one. Return len nums minus 1. I think this one's going to work. But it's on solution, right? It's on. It's not what is required, but I run the test case. Return 2. 1, 2, 1, 3, 5, 6, 4. And this one, it says 5, but it can either return 1 or 5. So mine will return the first one, so it will return 1. And this is going to be nums. This is going to be find peak element nums. And I run it, it pass. I think we'll pass. Right? The reason being, it's only 1,000, unless they set the requirement very, very stringent. Let's try this one. Let's try to return 0. Yeah. Unless they very stringent, it has to be log n. Yeah, it will accept, but the challenge is not that. Right? The challenge is not that. So this is the first, right? The first downward. The first downward signifies the existence of a peak, right? Not a peak, the existence of a peak. We can do this in ON, which this one gives us a 40 millisecond, or what's the ranking? 92% ranking. But that's not the challenge, right? The challenge is to do it in O log n time. Okay, so we have a better understanding of how the problem is. The problem is, given an array, right? Given an array, we want to find the first downward trend. So we can assume we have some upward trend, and then we have a downward trend. So we just want to know where that thing is. Now log n signifies that there is some binary search, maybe, involved. So what we can do is how do we binary search that? I mean, we don't even have to find the first one. We just need to find a peak, right? That means if we just pick any adjacent values, let's say in the middle, I'm just kind of thinking about binary search. If we find any two values, if I find the middle, I'm looking for here, middle will be this one, right? And I look around, right? I look around and I find out that I am bigger than the previous and smaller than the next. That means I'm in the upward trend. That means the peak will be in the second half. So in the second half, I do it again, right? So I move the left to here. So left is going to be here. And the mid will be here, so we'll compare again. So eventually we will, right? So if we give a value, it's either in the upward trend, a downward trend, or it is a peak. So if it's in the upward trend, we shrink the left. If it's the downward trend, we shrink the right. Yeah? And eventually they will meet in the middle, whatever value the middle is. So yeah, this is a binary search. And binary search will give us ON runtime. So let's try this, solution 2. I actually have another one, because we just tested another one. I think it's 3, 1, 2, 3. I think this is what we doing earlier. 3, 1, 2, 3, and this one gives us 0. Okay, so it's going to be binary search. We have low and high, right? Low, high equals 0, and len nums minus 1. What if it's constantly? Then they will then they will exit in the last element or the first element, right? So just say while low is smaller than high, mid equals low plus high divided by 2. And when I check if actually if I can no, yeah, we're gonna do this. So if mid is larger than 1, larger than 0, right? Because I need to check. Can I check only one side? No, I have to check on both sides. Hold on. Let me think. Maybe I only need to check on one side. What if I only check on the left side? If I'm larger than the left, then I might be the peak. So the peak will be on the, so we go here, right? And if the left is smaller, or the left is larger than me, then I'm definitely on the downward side. So I have to go left. So yeah, I think we only need to check on the left side, which means we can see if mid, because the left side will always be smaller when you're in the front, so it's always going to be smaller. So we can do this. If mid larger than 0 and nums mid minus 1, right? And nums mid minus 1 is smaller than nums mid. Actually, it's going to be this. If mid is equal to 0, right? Or, so mid is not equal to 0, mid will be larger than 0. Or at nums, mid minus 1 is smaller than mid. That means the peak, when they say the peak is on the right side, so when they shrink left, so left equals mid, all right? Else, which means m is not equal to 0, larger than 0, and nums mid minus 1 is larger, right? Then when I say not left, it's low. We call it low and high. So this is going to be high equals mid minus 1, right? Mid minus 1. We shrink here. And then blah, blah, blah. Once we're done, they will come out. And then we just return low, right? So solution 2, try it. Oops, we had an issue. Infinite loop. All right, what the hell? Let's try it. Print low and high. I think it's, yeah. Wait. Come on. Cancel. I think I have to check on the right side. I cannot check on the left side. Yeah, because high, so 0, 1, 2, 3, right? Low is 2, high is 3. So we go into here, low is here, mid is here, and mid minus 1 is smaller than mid, so low equals mid. That's why we're now moving. Oh, come on. Force quit. Open it again. All right, so it's not working. So we have to check. We have to move the left, right? We move the low. We cannot move the high. So we have to move the low, which means we're gonna check on the high, right? So mid equals this. So we say if mid equals minus 1. So we're going to say n equals len nums. This is going to be n. Let's say if this equals n minus 1, right? Or nums mid plus 1 is mid plus 1. Right, if mid plus 1 is smaller than mid, right? If mid plus 1 is smaller than mid, then we say high equals mid. Otherwise, low equals mid plus 1. Then this will work, because when you do a divide by 2, it actually shifts to the left side. So we always add the left side. This one shall work. Yep. So it's the same idea, right? So we just check the next value, right? If the next value is smaller than me, then I am on a downward trend, which means the peak must be on the left side. But I keep high, I don't move high. So I move when the next value is bigger than me, right? If the next value is bigger than me, then the peak we have to move mid plus 1. So again, we're in the tests, and it actually passes because 5 is one of the answer. Here, 5 is one of the answer, and 0, 1, 2, 3. 3 is one of the answer as well. So this one shall work. And we probably should change this into a set, right? So make it so that we can test different results. So this one pretty sure it's 0 or 3. So not going to be res in answer. There we go. All right, binary search. I don't think we'll actually run faster because the test case size is too small. Pending, judging. Yep. So that is binary search. This must be an easy question. Yeah, binary search is actually slower in absolute terms. So O log n, right? O log n and 48 milliseconds or 51% ranking. All right. Now let's take a look at the solution. It's an easy one. Set up as a medium. Well, 162. I might have done this, right? Have we? I don't know. LeetCode 162. Now I think if we follow the exact, no, I haven't done this before. If we follow the exact pattern, it's only Monday is easy. Linear scan. ON. Yep, that's that. Binary search, recursive. Iterative. Let's see. Middle, if middle larger than, I think that's exactly the same. Mid plus 1. But it doesn't include another check for mid equals. We're saying mid. Are we saying we're not gonna get to that position? What if it's like increasing, all right? And then the middle, and then next one is not, so low equals mid plus 1, right? High doesn't move, so every time we mid, and then eventually it will meet. That's true. That's true. Mid will not be n minus 1. Mid will not be n minus 1. So we can save this. Yeah. Well, mid not going to be n minus 1 because high starts at n minus 1, right? So mid will be the middle, and the high doesn't move. The only thing move is low, right? Is low. So the only chance for mid to get to n minus 1 is the high never moves, and the low just starts to getting closer and closer But before mid can be n minus 1 and hitting this line, we will hit this line first and we will exit. That's why this makes sense. Strict proof why binary search work here. Oh, it doesn't need proof. You think about it and it does work. Integer overflow. Well, I mean, you know what it's trying to say. Oh, wow, this is an old question. Oh yeah, this test case violates the condition. This is an old question. But he still shoots up to the top. 17. Yeah, I think a lot of people are doing this every day. I mean, for fun, all right? For fun. All right, that'll be it. It was quite straightforward today. I'll see you guys tomorrow. I'm pretty sure tomorrow we'll have to do it at night as well. Man, 2 days at night. That's gonna drain my energy. Adios.